So this is machine learning for cybersecurity. All right, unit 9. So data for TensorFlow. So here, this is the sequence of the discussion that relates to big data. And remember, in particular, when we talk about big data, we are using GPUs, right? So graphics processing units. Right? We have a few servers that we'll be using, and we have servers on AWS that we're also going to be using. So as we start with data for TensorFlow, basically, as I've said before, in machine learning, there's two main things: the data and the algorithms. Right? The algorithms that support the classifiers and the data, and usually getting the data into the code, into the program, is one of the most challenging parts. You can be 70 to 80% of the work is related to the data. So the learning outcomes for this unit are basically students will have a better understanding of data for TensorFlow. You can see that here. So they'll have a better understanding of data for TensorFlow. So data issues. To most practitioners, data collection is the most important issue in machine learning. It really is. Because once you become experienced with the algorithms, you really don't have to change them that much usually. There might be some new architectures, but you become well versed in the algorithms, and so there's less work there. But most of the work is going to be in your data, because it's usually a new data set, a new problem, and you have to frame it in a context that machine learning can understand. So some of the issues with data, we have obviously getting the data. Since we're talking about cybersecurity data here, cybersecurity data. All right, so getting the data, since we're talking about cybersecurity data, basically, we're talking about several specific sources. So obviously one of them is the network. All right, so we get data from the network. We have a lot of tools that we can use to get this data, such as TCP dump, right? Or we can use Wireshark. Wireshark is a useful tool that can allow us to, take PCAP files, and then there's code that we can write to extract those features. We also have just our own code, right, that we can write to extract data. So there's libpcap, right, and this is available in the C programming language, so C, C++. And this allows us to create just a general sniffer. It's a library. So getting the data for our purposes, it's mainly in this fashion. Network data, of course, is one source, but there are other sources, right? So we have just logs, right? So we can use logs. Everything that happens in a computer in the network can be logged, and then you can run code also to extract data from those logs. So that's another source where we can get our data. Additionally, we can get data from files, right? So whenever we have something like malware, right, we are talking about files that we are getting. And so these files could be attachments on emails, so we need to scan those. So every email that comes in needs to be scanned. Or we do scanning of files in operating systems. So basically some kind of scan mechanism of files in the OS, or scan email or downloads, etc. So different kinds of sources, but obviously we have to obtain our data from these sources. Then there's phishing attempts, right? So phishing, that happens via email. So again, we need some kind of a scanner for this. Usually for these tools, we have to use what is called a proxy firewall, or some kind of a tool like that, some server, that anything that's coming in through the network, so let's say there's a server here right? And now everything that's going from a switch, specific switch, to another, device, a router or whatever, let's say you have a computer that generates traffic. Everything before, it went directly on the line, but now this is connected, so everything has to go through the proxy and out of it, so that you can see if there's anything in it, and then scan it, etc. So these are ways of obtaining data that's related to cybersecurity, basically. All right. Once we have the data, then the next step is to clean it. All right. So rarely does the data, or never basically, is the data ready to go. Right. So usually you're going to have, if you're, let's say, go back to the network data over here, you're going to have what? Packets. All right. So remember, a packet is divided into different kinds of headers. All right. So you have an Ethernet header. Then you have the IP header. Then it's a TCP packet, a TCP header, and then we have the payload. All right, so all this data is encoded for the network to understand the data, but it's not encoded for machine learning to understand the data. So we have to do, we have to go in, clean, usually writing a Python script or something like that, that will take our PCAP files, and let's say this is a PCAP file in whatever format it's in. We write a Python script, right, and then Python will produce another file, right, a file that is already in the format that we need, some kind of machine learning ready. Right, so that's cleaning the data, removing anything that you don't need. Pre-processing is kind of the same idea. Pre-processing and cleaning the data, both steps go together. Just making sure that the data is, in the format that you need, right? So the format that's appropriate. So since we're talking about TensorFlow here, we're going to have to make sure that our data is, for instance, hot encoded, and it is in a matrix or vector notation. All right, once we have that data, we still have these two steps which relate to building a corpus. So usually whenever you have a problem in machine learning, everyone will always talk about the corpus. What does the corpus look like? What are the statistics of your data set, etc. All right, so building a corpus and annotating it. So there are several rules or considerations that have to be taken whenever you build a corpus. Annotating it means that you're going to use that corpus for supervised learning. All right, so in supervised learning, you're predicting, you're going to learn from annotated data. You have examples of, pictures of cats and dogs, right, that are annotated. Then you build a model. Then when you give it new pictures of cats and dogs, it's going to predict if it's a cat or a dog. So that's what annotating means, right? That humans actually go in there and they annotate the data and provide the labels for you. So that's actually one of the hardest parts of this whole process, because you need to have people, and people are not machines, so they're slow. When you're doing, for instance, things related to attacks to the network, for instance, it's even harder because it's not about reading a text or looking at a picture, but it's actually about running an attack, collecting that data versus running, let's say, regular traffic, right? So you have to collect the data. Now, whenever you're annotating, you also have a step called inter-annotator agreement. So this usually relates to, let's say two technical people looking at certain network traffic. One person says that network traffic is related to malware, and the other person also says that network traffic is related to network traffic, to malware or anomalies. So in that case, both of them agree that they're both anomalies, so there's something called inter-annotator agreement. Two humans agreed that they were both anomalies. However, it could happen that you have some network traffic and one technical person says, yes, this is an anomaly, but the other one says, no, I don't think this is an anomaly. In that case, they don't agree. right? The two annotators do not agree, and so you have disagreement. So if two humans have disagreement, imagine how hard it'll be for a computer to distinguish between samples here. So basically, inter-annotator agreement is a way of establishing a metric of how subjective your data set might be. Right? So that's really what it is. And it's something that a corpus, a well-built corpus, should definitely have inter-annotator agreement. Kind of tells you how subjective it is or not. All right, so those are some of the data issues associated with the data set. All right, so data sets, data can be obtained from, in general, whenever you're talking about machine learning in general. So machine learning in general. Data can be obtained from the web, such as text, from Twitter or web pages, for instance. This is a common data sources, especially if you're doing something like natural language processing in NLP. Data sets can also be obtained. So, this is the source for our cyber, as I explained. Our sources can be these ones, right? So the network, logs, files, phishing, email, etc. Now, additionally, when for academic purposes, let's say for us that we're studying, specific data sets can also be obtained from machine learning libraries, right? And this is something that we've seen throughout the class, or will continue to see, that all the libraries, TensorFlow, SKlearn, for instance, Weka, they all contain modules, specific modules that contain data sets. The well-known standard data sets, are available there. So we'll see some code of how this dataset module is available and it can be used. So dataset modules in SKlearn, for instance, can be obtained to get things such as Iris, the famous Iris dataset built by Fisher, right? Fisher. Or there's also MNIST, which is another common dataset, more useful for big data, because whereas Iris only has 150 samples, 150 samples, and it has 4 features, MNIST has about 70,000 samples, and it has 784 features. All right, so in terms of something that is big data, this is a little bit more useful. So how do you get the data? This is standard generic sklearn code. All right, so here basically you use the module datasets. Okay, and then you do .load iris, for instance, and then you create an object iris, a variable, and then now you have your data in that variable. However, whenever you have the data, then the next step is you want to proceed to, identify what are the features and what are the classes, right? So you want to separate that out kind of into Y and an X, right? Because you're going to be using these separately. So you can see here iris.data is has conveniently a way to separate these things automatically for you. So this is very convenient when you're just trying out things, getting our data going. So additionally, slicing, I believe it's a topic that I've probably discussed in previous lectures. Slicing here just means that before the comma, that's all the rows. So whenever we have a colon, that's all the rows. And then we can provide a list of the columns that we want, such as 1, 2, and 3, or maybe we just want 1 and 3. And so that's what we're doing here, and this is called slicing. All right, so this is the data sets. Another important issue is format. So in general, you usually want to create files that are either comma separated, or they are tab separated. So the tab is something like this, right? So tab. Now, whenever you're doing applications like let's say you had data in the payload of a packet. Well, it's possible that in that payload you could have a comma. All right, and then usually you don't want to split on that particular comma later on. And so that's why it is sometimes better to have a tab, because it is less likely that you would have tabs in the payload. It's a very uncommon character, and so that's the reason why people create these. But in general, most data sets that you create are going to look kind of like this. All right, and if you notice, the commas here basically separate so that you have the first one is the class, and then after you have features F1, F2, F3, F3, F4, so that they look like that. So that's kind of the idea. All right, and so that's what the commas do. In all data sets that you create, it's probably useful to go from whatever data you have, PCAP, logs, email, files, etc., whatever your network data might be, it's probably good to always have the goal of converting your data from whatever format they have in here into that. All right? That, as I said, that's probably the first step. There are other formats after that, but this is usually the most intuitive and clear. Now, important things to consider here, you need to make sure that things are aligned. So like if you missed this class, let's say that you made a mistake and you missed it, and now this row is 6.0, 2.9, 4.5, 1.5, and then let's say that there's a comma there and there's a null value here. Well, this is actually completely wrong, because now this 6 is in the first column. So what machine learning will think is that that 6 is the class, which is not. It was supposed to be feature 1. And so just because it shifted a little bit to the left, right, you've caused a problem, and now your machine learning algorithm does not work. So you want to avoid that, and you want to be especially careful in making sure that things are properly aligned like this. All right, and that is one of the key things, actually. This is a key thing that a data scientist must do and must worry about. All right, there's that well-known expression, right? Garbage in, garbage out. So you want to avoid, if you have errors like this in your data, then you're not doing anything with your machine learning. So you want to make sure that your data is very clean and good like this, and then you can trust that the algorithms will do their job. All right? So this is a very important aspect, and it's something that a data scientist must do. NumPy is one of the important libraries in machine learning in general. All right, so NumPy is for anyone that has had experience with something called MATLAB back in the day. Right, MATLAB really is still a very good application for doing vector and matrix operations. And it's efficient. So this is something that, like a linear algebra, right? So if you can do linear algebra in this environment. So for a long time, Python was not really able to do this, efficiently at least. And so people still had to use MATLAB. But what they really wanted was a MATLAB in Python, right? And that's what led to NumPy. All right, NumPy, it's really the solution so that now you can do MATLAB in Python, which basically means that you can do linear algebra efficiently. It turns out that a lot of the math behind data science really can be done through linear algebra by expressing our equations, etc., our values as systems of equations, so matrices and vectors. So once the data is in matrix data, right, because this is how we are going to load the data. So that if you look the previous slide, this data set that we have is really a matrix, right? That's really a matrix right there. And so once we have that matrix, it can be processed efficiently through the NumPy array as a NumPy array matrix. So we're going to have some code that takes the original, which is just a two-dimensional array, and converts it into an efficient NumPy array. So this means that it is no longer just an array, right? But instead, it is more a vector or a matrix, as in linear algebra, right? And so, whereas before, for that array, you had to, if you wanted to iterate through it, you had to do for I in range, of I, and then for j in range of j max, right? This is I max. Right, so this is how we had to write the code before. But if you think about it, writing Python code with for loops like this is very inefficient. All right, so a much more efficient way is to create a NumPy array or NumPy matrix and then use different coding style, much more efficient, to be much faster, to obtain better results. So now, many operations are now simplified, like extracting certain columns and rows. We no longer have to iterate through the matrix and extract the values. We can just use slicing, right? Where slicing is this code over here, right? So we can just really efficiently select what we want instead of writing for loops. So here's the code for it. So we have, for instance, we read a data set, a .csv file, right? We add it. We create we create a reader basically. We read the file. Then we do NumPy load text using the file descriptor. We can specify that the delimiter is comma, so it's a comma separated file, and that we want to skip the first row, which usually indicates the column names, right? So it would be basically these in red class F1, F2, F3 that we are just getting rid of. Okay, so we have the matrix and matrix data, right? And then here we can, do various operations. So here I want to know the length, for instance, of the first column for all elements in it. So that gives me what? The number of rows, right? So this A is actually the number of rows. So that's a useful little trick. And then you can do print, or rather, number of features. So it's actually... Oh, that's right. So I'm sorry. So this is 0. So it would be 0, 1, 2, 3. So I'm actually saying just grab that row, right? And once I grab that row, then I select all the elements in that row, by saying all. So actually, sorry, yeah. So this is not rows. This is columns. All right. So this is columns here. All right, and so by saying columns, we can actually, that's the same as features, right? So those are the because, if we go back to this, columns are class F1, F2, F3, F4. The only thing is if we want to know the number of features, it might be this minus 1, right? So minus 1. But that gives us the number of features, all right? Then it, that's one little trick to get some of the values. Now, if we want to slice out some more data, let's say that both the features and the classes are in there, then here, for instance, we can extract just a vector for the classes by saying all rows, so all rows, and for all rows, extract just column 19, so that maybe it's the last column, right? So you extract that entire thing, and now you have the classes for those samples. Here, if you want the X data, you can just say, again, take the matrix, grab all the rows, and then here we say all values because we specify colon. There's nothing here, so that means from 0, from beginning, all the way to 18. So we establish a range, basically, of columns that we want. All right, so that's the code, basically, to load, a CSV convert it into a Numpy array, and then perform various slicing methods. So here, this is a summarization of the previous slides. So in the previous code, we can see that we can calculate the dimensions of the matrix, and I explained that here by getting A. All right, so that's the number of features plus the class. Now the following piece of code shows how the data can be read with the npload txt and then sliced out into two matrices, which are x test and y test. So we've seen this before, but usually remember that we divide the data always into actually 4 sets, right? Because we're going to have training, and then we also have testing. But within this, we always have x and we have y, right? So we have x and we have y, right? So we will always have about 4 data sets that we are using. All right, so this is, I've already talked about this. I still need to work on these slides, clean them up a little. And then here, I already described this part as well. So I probably can get rid of this. Feature scaling, so we're still dealing with data issues. All right, so other data issues that we are concerned with are feature scaling. Feature scaling is very important to achieve good results in classification tasks. All right, so feature scaling is basically you have 3 features, let's say F1, F2, F3. Right, and you have the values for this one, let's say, and this is a good example. We have packets, right? So we have a source port. This is the source port of a packet. This is the destination port of a packet. Now, what do we know about this? We know that ports go from 1 to 65,000. So the scale of values is from 1 to 65,000. And the same for this one, you know. So no issues there. They both have the same scale. But then it could turn out that we have another class, or sorry, another feature, and it's just the protocol. Right? So it's just the protocol of the packet. And it turns out that the protocols that are being used in these packets go from 1 to 100. You see? So that's very limited, right? That's very limited. So if we plot this as a graph, these 3 in the vector space model, what we end up with is something like this. So here, this is a vector space that has perfect scaling. But if this is F1 and this is F2, which go from 1 to 65,000 and 1 to 65,000, the problem is that F3 is only from 1 to 100. So you end up with just an axis that's pretty short. Do you see that? And so what usually happens in machine learning is that these 2 features are going to totally dominate this other one, right? So because it's easier to see a point, like that, versus a point, the difference between that point and that point, right? So there's like a very small margin of difference. And so that makes it much more difficult. So scaling is where you're going to convert from this to a vector space model of equal axes. So that's easily done by setting it 0 to 1, 0 to 1, right? And then you just represent the percentage that you have, right? So that's an important one. So feature scaling is very important to achieving good results in classification tasks. For example, in principal component analysis, which is one of the methods we should discuss, has to do with the dimensionality reduction. It's a feature reduction technique. Feature scaling is important. That is to say, if you don't scale first, then principal component analysis will not do its job as well as it could. Right? So the purpose of PCA is to project data to a vector that captures the most variability in the data. Right? So what I was saying here, this variability. You're not going to capture it, whereas here, between these 2 points, there's all this variability. That chunk of space is much bigger than that. Right? So you're not going to capture how things vary within that range. So if the features are not scaled properly, one feature could dominate over the others and therefore be considered as the most variable feature, which is not entirely true. It could turn out that values here go from are in the range of 65,000 versus 60,000, and the values in the other one are from 2 to 99. If they are not scaled, this is only a difference of less than 100. This is a difference of 5,000. So it seems like this one dominates. But in the grand scheme of things, this is only 5,000 out of 60,000, right? Whereas this is basically 98% of the entire variability, right? From one end to another end. And so that's what I'm saying. So you want to equalize these as much as possible, and that's why you use feature scaling. Now there are several built-in techniques that are available, and those are algorithms, etc. But really, we're just going to use the standard scaler that's available in our code. So again, a little bit more about feature scaling. So with feature scaling, features with real valued numbers from any range can be mapped to other ranges, as I said. So, such as from 1 to 65 or 1 to 100, both of these can be scaled to a range of -1 and 1 or a range of 0 to 1. You just want it to be consistent for all the features. So this is performed for all features so that no one feature will dominate in the model. Other classifiers and deep learning models are also susceptible to feature scaling, so it is very important. Now here's an example of the code, so very standard. This is with SKlearn, right? So SKlearn in Python, you take the standard scaler, create an object, then you're going to give it your data set, xtrain, right? Xtrain. And you're going to, again, fit a model. And then once that model is fit, you apply that model to everything else. So you're going to apply it again to train, but also to test, right? So that it is consistent in the scaling. And that's simply done by doing an sc.fit and then an sc.transform. Once you've done that, then you end up with your xtrain normalized and your xtest normalized, and those are the data sets that you use going forward, right? So because the data is now scaled. Okay. One hot encoding. This is particularly important for Tensorflow, and this only relates to the classes. So, let there be no confusion about this relating. So one hot encoding relates to Tensorflow and only to the classes. That is to say, you do not apply one hot encoding to the features. Okay? So going back to our initial data set here, this one, you would only apply one hot encoding to the first column. You do not apply it to the other 4 columns. Okay? Now, all that happens with one hot encoding is that you're taking your data that looks like this, where you have class 0, class 1, class 2, and you're converting it into this, where now, if you notice, everything is a vector of 1s and 0s, where you have a 0 for everything and a 1 just for the corresponding number. So if you look, for instance, 0 is the first position, so that has a 1. 1 would be the second position, so that it has a 1 here in the middle. And then 2 would be this one here, so this goes like that. 2 is the third position, so it has a 1 there, and the other ones are 0s. So that's what one hot encoding achieves. Here's a little algorithm of how that works. However, it's not necessary to write. This algorithm is not necessarily the most efficient, but it's certainly clear. However, there are one hot encoding functions that can be used. I don't have it here. All right. So, and I don't remember, but it's something like tf.onehot, I think. And so you give it y, and then it's going to be something like that. Right, and simply then, what you might imagine is it takes this y and produces this y 1 hot, like that. All right, so that's the function over here with the code.